Hello, and thank you for joining us. Today's webinar topic is Effortlessly Achieve Inorganic Carbon Removal Requirement for Standards Methods 5310C. Our presenter is Steve Proffitt, TOC Applications Chemist for Teledyne Labs. If you have any questions, please feel free to submit them throughout the presentation or email Steve directly, and he will follow up with you after the webinar concludes. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Steve Proffitt.
Thanks, Shelley. Hello, thank you for attending this webinar today. My name is Steve Proffitt. I'm an applications chemist with Teledyne Labs at Teledyne Techmar in Mason, Ohio. I specialize in product marketing and method development for our TOC analyzers, of which we have two high temperature combustion analyzers and also a UV Persulfate TOC analyzer. Today we'll be looking at inorganic carbon removal requirement for standard methods 5310C. With the Fusion UV Persulfate TOC analyzer set up with the proper configuration, this requirement can be surpassed effortlessly. So before we start, just for reference for any other instrumentation requirements you may have, Teledyne Labs consolidates CTAC, Techmar, ISCO, Hansen, and Lehman Labs for instrumentation essential for diffusion, elemental analysis, physical testing, pumping, automated liquid handling, GC sample prep, chromatography, dissolution, and evaporation. The agenda for my presentation starts with a brief introduction to standard methods. Next will be a TOC overview. Then we'll look at the Fusion UV Persulfate TOC analyzer and the methodology used for acquiring TOC results. Inorganic carbon removal requirements according to 5310C will be discussed. Next, I'll present a demonstration of IC removal methodology and results achieved in our applications lab. I'll then highlight specific factors that will determine success in passing the IC removal requirement. To complete the presentation, I'll highlight the features and benefits of the Fusion. Standard methods is most known as a shortened form of standard methods for the examination of water and wastewater. And method 5310 is the method for TOC analysis. Standard Methods is a well-known publication and is used in countless laboratories around the world. Most methods within the publication have been endorsed by numerous regulatory agencies, including the US EPA. Standard Methods was first published in 1905. Since then, and through 24 editions, Standard Methods has included hundreds of analytical techniques for the determination of water quality. These techniques have been developed by over 250 water quality researchers that make up the Standard Methods Committee. This committee is charged with the review and approval of analytical methods. Top scientists in the water community come together to produce Standard Methods, which is a mutual publication of American Public Health Association, American Waterworks Association, and Water Environment Federation. 5310A gives the overview of TOC analysis. Organic carbon in water is composed of a variety of organic compounds in various oxidation states. The following methods can be used to characterize these fractions by further oxidizing these carbon compounds: biological oxygen demand, chemical oxygen demand, and assimilable oxygen carbon. Organic carbon. In contrast, TOC is a direct expression of organic carbon content compared to the other methods. TOC measurement in a sample is independent of the organic matter's oxidation state and doesn't measure other organically bound elements or inorganics that can contribute to the oxygen demand measured by BOD or COD. TOC is much faster, more convenient analysis. For UV persulfate methodology, typical runtime is 15 minutes for a triplicate analysis. Analysis time for other methods is significantly longer. BOD test results take 5 days. COD test results typically require 3 hours to complete. And AOC analysis is the longest at 7 to 14 days. There are two fractions of total carbon that exist in a water sample, organic carbon and inorganic carbon. The instrumentation and methodology used in measuring TOC must distinguish between the two fractions of total carbon to determine TOC content. In organic carbon, or TOC, all carbon atoms are covalently bonded in organic molecules, including synthetic materials, organic products, decaying matter, and living organisms. Inorganic carbon consists of cyanides, elemental carbon, carbonate, bicarbonate, and dissolved CO2. Just as there are two fractions of total carbon in water samples, there are four fractions of TOC that can exist in water samples. Purgeable organic carbon is the fraction of TOC removed from an aqueous solution by purging with gas. Non-purgeable organic carbon is the fraction not removed by purging with gas. Dissolved organic carbon, or DOC, is the fraction of TOC that can pass through a 0.45 micron pore filter. And suspended organic carbon, or particulate organic carbon, which is the fraction of TOC retained by a 0.45 micron filter. Method 5310C is for TOC analysis by UV persulfate oxidation. The UV persulfate method is suitable for samples with lower values of TOC, as the instrumentation will provide lower detection limits. Generally, these samples are cleaner in nature, ranging from surface waters to water treatment facility samples to purified waters for pharmaceutical production. Our UV persulfate instrument diffusion is pictured on the right. To achieve a TOC result using diffusion, the IC fraction of the sample must be removed. IC removal occurs automatically inside the IC sparger. Phosphoric acid is added to the IC sparger along with the sample. The acidified sample is then sparged, removing the inorganic carbon from the sample. After IC removal, an aliquot of sample is transferred to the UV reactor, and with an addition of sodium persulfate along with sparging, the organic carbon is oxidized and converted into CO2, and then swept into a NDIR detector for quantification. In many water samples, the IC fraction of the total carbon contained in the sample may be many times greater than the TOC fraction. The IC fraction can be eliminated by adjusting the samples to pH 4 or less to convert the IC species to CO2. Samples are normally adjusted to pH 2 or less. However, this may maximize the hydrophobic molecule loss to the sample vessel walls. Adjusting to pH 4 minimizes such losses. Reaching the correct pH value in a sample will determine if all carbonate materials in unfiltered samples completely dissolve, and then will be effectively removed through sparging before TOC analysis. IC removal efficiency must be verified initially to confirm that IC is effectively removed from the samples. This must be done at initial instrument performance validation, during routine QC scheduling, and after any maintenance that may affect the technique for IC removal. For the IC removal requirement, according to 5310C, a 102.5 ppm IC test solution is prepared and analyzed to confirm that the result is less than 1/2 of the laboratory's minimum reporting level. The standard IC removal check solution as presented in Standard Methods 5310 is prepared in 4 separate stock solutions. Due to inorganic salts not being soluble in a single concentrated solution. Standard Methods also notes that the IC removal check may be performed on a different matrix, but the IC level in the check sample must be higher than those in the unknown samples. And that's documented in 5310A, section 5B10. Okay, this slide is a bit busy, but these are the 4 solutions needed to prepare the IC test solution according to Standard Methods 5310. There are 9 different chemical compounds used to make up the final test solution. I prepared my test solution just as described in 5310. And if you look closely at all the compounds here, solution C is actually the only compound that contains inorganic carbon. The other solutions contain minerals and impurities that may represent an actual surface water, drinking water, or environmental sample. As you go through, you can see you've got magnesium sulfate in solution A, then ammonium chloride, calcium nitrate, potassium chloride, sodium chloride. So there's 9 different compounds that you have to purchase, and you must be sure to get the most pure form, or you can add unwanted carbon to your IC standard. Once the final solution is prepared, it must be acidified to ensure all compounds are dissolved. 4 different acids were tested for comparative results. Phosphoric acid provided the best results by far. The other acids will create interference in the analysis and produce non-passing results. Also, a 21% phosphoric acid solution is what is recommended for the acid reagent for the fusion. And using the same acid in samples and check standards will provide more consistent results. Okay, this is the method I used for achieving an MRL of 1 ppm. The fusion was calibrated from 0 to 25 ppm using a 2 milliliter sample volume, 1 milliliter of 21% acid reagent, and 1 ml of sodium persulfate reagent. All but one of the variables in this method are preset within the drinking water method in the Fusion TOC TechLink software. Only the sample volume was decreased to allow to calibrate to a higher level at 25 ppm. The calibration was performed using the auto calibration feature of the Fusion, in which lower level calibration points are automatically diluted from one stock calibration standard. The 25 ppm stock solution prepared from potassium hydrogen phthalate was used for the auto calibration. Once calibrated, 2 IC removal standards were analyzed, followed by a 5 ppm calibration check. And here's the 7-point calibration from 0 to 25 ppm that resulted. As you can see, the linearity is excellent with a coefficient of correlation at 0.99979, as well as a low y-intercept value at 2.98. To validate a 1 ppm MRL, the IC removal result must be less than 0.5 ppm. My results were 0.41 and 0.36, with the 5 ppm cal check coming in at 5.12. Next is the method I created to achieve a lower MRL at 0.5 ppm. Beginning with the drinking water default method defined in the Fusion's TOC TechLink software, the sample volume was lowered from 6 milliliters to 2 milliliters. Acid volume was increased from 1 to 2 milliliters. Reagent volume was increased as well to 1.3 milliliters. The IC sparge time was increased from 1 minute to 7.5 minutes. Pre-sparge time changed from 0.2 minutes to 1.5 minutes. And the IC prime volume was changed from 2 milliliters to 4 milliliters. The additional acid, along with longer sparge and pre-sparge times, will maximize the IC removal potential of the analyzer. The same calibration range and technique were used. Again, the results show excellent linearity with a 0.99988 R-squared value and a low y-intercept. The analytical results, the 5 ppm calibration check was very accurate at 4.89 ppm, and the resulting IC removal checks all passed at 0.2, 0.19, 0.21, 0.21, and 0.19. Results needed to be less than 0.25 ppm for a 0.5 ppm MRL. So for optimal results when calibrating, the y-intercept must closely match the TOC raw value for reagent water and the 0 point on the calibration curve. For the 1 ppm MRL method, the y-intercept is 2.99. The 0 point on the calibration curve is 3.04. Reagent water results averaged around 4, so those are very close to matching, and that is essential. For the 0.5 ppm MRL method, the y-intercept is 6.09. The numbers will be a little bit elevated due to the increased amount of acid in persulfate reagent. 0 point on the calibration curve is 5.38. Reagent water results average around 6.5. Another crucial configuration element to ensure success is that the IC removal standard must be set up in the schedule as a check standard. Setting up as a check standard will subtract the y-intercept before calculating the ppm value result. This calculation subtracts the carbon contribution from the persulfate reagent, as well as the carbon contribution from the reagent water used to make the IC removal standard. So considering any component used for preparing the IC removal standard will contain trace amounts of carbon, the utmost care must be observed for cleanliness. Glassware must be meticulously cleaned. Vials should be certified clean for low-level TOC content. Chemicals used for preparing the IC removal standard must be ACS grade or better in order to minimize any contamination. Pipettes, pipetters, and pipette tips must not contribute excess carbon to the standard. Avoiding contamination is a main priority for success. As I mentioned earlier in this presentation, and will again remark on this important note regarding the IC removal check standard, this can be found in 5310A, Section 5, QC applicable to all 5310 methods, Part B10, as read directly from the method. Inorganic carbon check. Prepare a 102.5 milligram per liter IC test solution based on bicarbonate calculations and impurities, and analyze the solution to confirm that the result is less than 1/2 mRL. The IC removal check may be performed on a different matrix, but the IC level in the sample check must be higher than those in the unknown samples. This is an important deviation that's allowed because the recommended IC removal check standards, as I mentioned earlier, is composed of 9 different compounds that may either not be available in certain areas or not available at the necessary purity. Sometimes this IC removal requirement can be difficult to pass, and this gives laboratories some room to figure out what works best and still be compliant. So in conclusion, the Teledyne Labs Fusion UV Persulfate TOC Analyzer is an exceptional analytical instrument for TOC determination by standard methods 5310C. And following the guidelines in this application note will ensure that your laboratory can successfully meet the IC removal requirement within the method. Thanks for the opportunity to share this information. My name is Steve Profit, and I welcome any questions anyone may have. Please contact me at stephen.profit@teledyne.com for further information.